All right, so picking up where we left off before the test, example 7, we didn't do E or F, but we'll do E now, S of t. So the function's name is Steve, S for short, and the independent variable is t. T for Texas, I guess, right? We want to find the domain. Notice we have a radical and a denominator with a variable underneath it, and it's the square root radical. That's important because if it were cube root, negatives are okay. So after we finish this extra practice worksheet, this should be easy for you, right? We know 3 minus 2t squared has to be greater than or equal to 0, and the entire denominator with the radical intact can't be 0, right? We get in the habit of doing that. Now again, if you're fancy or you have a keen understanding of what's supposed to happen here, you could set it up with a single inequality, can't you? You could actually say that 3 minus 2t squared has to be strictly greater than 0, and that would take care of both cases. But we won't be fancy here. We'll just do both of them. Now on this one here, can I solve it algebraically? No, it's a parabola. It opens down, right? Now, in this case, it doesn't really factor nicely. So what I'm going to do off to the side, since it doesn't factor, I'm going to set it equal to 0 off to the side. Because remember, there's a huge difference. When I set it equal to 0, I can start doing algebraic things to it. Whereas if it's in an inequality, I can't. So what I want to do is separate the variables. I'm going to bring the 2t squared to the right side to make it positive. I'm going to divide through by 2. And now when I take the square root, I'm going to flip both sides. And when I take the square root, I can't forget to remember to do what? Well, it's an equation, so there's nothing to flip here. What I was looking for is plus or minus, right? Plus or minus the square root of 3/2. Not the prettiest roots, okay? But those are the two roots. So again, because I set it equal to 0, I'm allowed to separate variables and take the square root of both sides. Now I can graph it. Here is negative square root of 3/2. I don't know exactly where it is. And here's positive square root of 3/2. I don't know exactly where it is. But I do know that they're symmetrical. One's negative, one's positive. And this parabola opens what? Up or down? Down. Good. So as I draw my parabola, I'm going to draw it like this, passing through those roots. And then I return to the inequality. And I come up here, and not surprisingly, I want to know where it's greater than or equal to 0. So that's above the axis. So for the inequality, it can equal square root of 3/2, and then it's going to be everything in between, and then positive square root of 3/2 is included. Okay? So that takes care of the demands. If you want to write it, it would be like this. Okay, negative square root of 3/2 less than or equal to x, less than or equal to positive square root of 3/2. It's the and case. But as you work on the right-hand side and you square both sides, the radical is already isolated. So when you square both sides, you're going to get that. Now, if you keep working algebraically, it's going to look a lot like what we did over there. You're going to get t cannot equal plus or minus the square root of 3/2. And they're not going to be extraneous. You can check them. They do actually cause a 0. So now we combine the results. The easiest way to eliminate plus or minus the square root of 3/2 is to never even include them, right? So you can actually do this with Notability. It's great. Just come back over here and pick like a little white tool, and you can now make this an open circle, right? Oh, you could use the partial erase tool as well. Many ways to do the same thing. Yeah, I like that. Yeah. Okay. Let's go ahead and write our answer then. Uh-oh. So you go ahead and without me. The domain of S is going to be this Corpy. Hi. Yes, she is. Okay, we'll do. Student services with your stuff, they said. Back office, yeah. D sub S is the set of all what? X or T? T, right? Such that T, well, if we're going to do it as an inequality, remember all we have to do is take away these equal signs over here. Okay, so it'll be negative square root of 3 halves, strictly less than t, strictly less than square root of 3 halves. The interval notation is a little bit nicer. We'll say t epsilon, and then we'll do parentheses, negative square root of 3 halves, comma, positive square root of 3 halves. So there's a good example of why we like to put the t epsilon in front, or x epsilon if it were x, because without it, notice this interval, this open interval, looks like an ordered pair. So having the t in front keeps it in the context that, hey, that's not an input, comma, output value. Those are two input values from the first to the second. Okay. Comments or questions on that one? It's kind of fun to use something, bless you, other than X for a change. Bless you. All right, now this one says to verify in your calculator. I don't know why I do that. It's just like, silly. I guess we can. But if you notice, this one is u of n. The function's name is u. You are the function. How about that? The independent variable is n, and it's letter F. So there's like a subliminal message in there, right? Math is fun, yeah? All right, so here's the deal. We know this is a complex fraction. We know that we can simplify complex fractions by doing lick 'em over lick 'em. Problem is when you do lick 'em over lick 'em and you simplify it, sometimes you change the domain. Okay, and doing that can be helpful for the purposes of evaluating things a lot faster in the simplified form, or sketching the graph of it a little bit faster when it's in simplified form. It's easier to use. Problem is, though, this is the actual function. It is what it is. So if we change it, we have to make sure that we're still talking about the original guy, meaning we need to find the domain of the original function first, okay? Let me show you why. There's no square roots in this one, is there? Or are there? No. But we do have denominators. We have the miniature denominators, n and n, and then we have the grande denominator, which is that. Yes? So let's go ahead and set all of our denominators not equal to 0. Bless you. Bless you. N cannot equal 0. Do I need to worry about the 2? 2 is never going to be 0, right? 2 is technically a miniature denominator, but he's never 0. So n cannot equal 0. Well, that's one of the restricted values. I don't need to solve. And then the other denominator, the grande denominator, because it's below this line, is n minus 1 over n can't be 0. Now, this is the first time we're dealing with a rational function not equal to 0. How do we solve this equation or non-equation? Is it okay, and you might have learned this in Algebra 2, is it okay to multiply both sides by n? Because look, they would divide out here, and 0 times n is that. And we would end up with n minus 1 cannot equal 0. Is it okay to multiply both sides by n? No, it's not. If n were a number, it's okay to multiply both sides by the number. Losing a number is not a big deal. But when you multiply both sides by a variable, you lose information, okay? And you don't want to do that. So if you learn that as an algebraic technique, I'm sorry, but we have to correct your thinking, all right? I'll just say this right here. When you lose a variable, comma, you lose information or solutions, if you want to abbreviate that. So here's what we're going to do. We're going to still get to the same line of n minus 1 can't be 0, but we're not going to do it by modifying the function above and multiplying both sides by n. We're going to think about it this way. A fraction is equal to 0. A fraction is equal to 0 when the numerator is equal to 0, okay? For instance, 0 over 5 equals 0. 0 over negative 3 equals 0. 0 divided by a number is 0. So whenever you have a single fraction equal to 0 and you need to solve it, all you're going to do is set the numerator, whatever it is, equal to 0. That keeps the original function up above intact, okay? But we're solving it in the right way. It's going to end up being the same. It feels exactly the same, but you're not getting rid of a variable, okay? So when is a fraction equal to 0? When only the numerator is equal to 0, right? So set your numerator not equal to 0, and now we can solve when we get n cannot equal 1. And those are your two restrictions. We don't need to test anything out because, you know, we didn't square both sides. So your domain, d sub f, or d sub u, sorry, d sub u, or your domain, if you will, it's the set of all n such that n is not equal to 0, comma 1. Or if you do interval notation, it's going to be the set of all n in the interval, negative infinity to 0, step over 0, go to 1, step over 1, go to infinity, okay? That is the domain of the function. There's two values that make two different denominators 0. One makes the miniature denominator 0, and one makes the big denominator 0. All right, now let's go ahead and simplify the complex fraction. Okay, come back up here, simplify the complex fraction. I'm going to show you why it's so important to find the domain first. We're going to multiply by the LCM of your miniature denominators. What is the LCM of 2 and n? It's 2n, right? 2n, 2n. Put it over 1. I don't have any room to work vertically, so I'm going to work horizontally here. When I distribute in the top, your n divides out in the first one, and you're left with 2 times 1, which is 2. When you distribute to the second one, your 2 divides out, and you're left with 1 times n, which is n. In the bottom, there's nothing to distribute to. There's only one term, so your n's divide out, and you can actually swipe them out there because you're not distributing it. You're not using it twice. And we're left with 2 times the quantity, n minus 1. Here is the cleaned up version, okay? That's the cleaned up version. And of course, if you wanted to distribute the 2 in the bottom, you're more than welcome to. If you were to simplify, don't forget the equal sign. If you were to simplify, when you work left to right, you do need the equal sign. Don't forget that. If you were to simplify and then find the domain, would you get the same domain as the original? N can't be 0 or 1. No, because look what happened. Now we only have one denominator, and there's only one factor in the bottom of the variable. What value makes n minus 1 0? 1. If you were to find the domain of it after you simplified, you would get n cannot equal only 1, and 0 is permissible, okay? But that's not what the function is. So if you were to simplify, there's still a built-in safeguard against using 1. The function still does not permit you to use a 1. This is where you would want to put a comma off to the side and say, hey, don't use 0, okay? You can use this to give you the same values as the original, just don't use 0. I know when you plug it in, it's going to give you an output, but it doesn't work in the real function, okay? So you would warn people about that. All right. There you go. So in general, find the domain first and then simplify. When in doubt, find the domain first. Because sometimes when you simplify, you change it. You change its phenotype. You don't change its genotype. You don't change its genetic makeup. Still can't be 0 or 1, but you change its physical appearance. Okay? All right. Any questions then on anything so far? The word of the day is inculcate. We already talked about that, to impress upon you how important it is to find the domain first before you simplify. The quote of the day, I put it up. Here it is. The nice thing about being a celebrity is that if you bore people, they think it's their fault, right? Henry Kissinger said that. A minor celebrity, Henry Kissinger, a politician. Okay. It's true, right? Because you're like, oh, they're famous. They must be an exciting person, and I'm sorry, it must be my fault, right? If only the tables were turned. All right. Here we go. We are now going to define the discontinuities. we know that, and we've talked about this, we know that when you get a division by 0, just a division by 0, you're getting a single value that's not in the domain, right? A single value. Could be more than one. But when you get a single value, that means like if x can't equal 0 or 1, like we just saw, the graph lives to the left of 0 and the graph lives to the right of 0, immediately to the left and immediately to the right. So when you get to 0 as you're sketching it, you have to stop and you have to get to the other side. It interrupts the flow of the graph. It interrupts the continuity of the graph. So we call those values that give you division by 0 discontinuities. We don't call the values that give you negative discontinuities because there's many values that give you a negative. And that's a whole span of values that don't work. A discontinuity is a single point that interrupts the flow of the graph. And that's going to come from division by 0. Okay? So let's go ahead and read what's in the box. For any function f of x, any value of x that results in division by 0 is called a discontinuity of the function f. So called because the graph exists immediately to the left and immediately to the right and therefore interrupts the graph. Sounds like something you've heard before. Inculcation. These discontinuities are going to be classified as one of two types. Either the removable point discontinuity, also known as a hole, or the non-removable infinite discontinuities, also known as vertical asymptotes, also known as, in this class, VAs. So it's okay if you know their nicknames, if you refer to them by their nicknames, right? My nickname is Kevin, but my real name is also Kevin, right? So sometimes you don't have a nickname. Actually, I do have lots of nicknames, but they're like stupid and doofus and dork, you know, idiot, right? Should I go on? No. So if you know the nicknames holes and VAs, I'm totally cool with that. But you still have to know their formal name in the back of your mind. Removable point discontinuity and a non-removable infinite discontinuity. One's a hole, one's a vertical asymptote. Vertical asymptote is a lot to write. So we'll say VA. By the way, there are other types of asymptotes. You might have heard of a horizontal asymptote, maybe even a slant asymptote. There are also quadratic asymptotes, cubic asymptotes. There are all kinds of asymptotes. The only asymptote that's a discontinuity is a vertical asymptote. And the reason is because a vertical asymptote runs from north to south forever and ever and ever. And you can't get from one side to the other when you go left to right without picking up your pen or pencil and getting to the other side. Okay? So let's go ahead and draw a little picture. Let's talk about the holes. Yeah, I know. I do that all the time. Let's say, yeah, it happens. Let's say you have a function f of x, okay? Notice this function, here's x equals c right here, okay? If you go up, there's x equals c. I'll even put a solid dot there. There's x equals c, all right? It's defined. It's continuous there, isn't it? It looks like it's continuous. I just drew the function straight through without lifting my pen or pencil. Now, pretend you're on Dora the Explorer, right? And you're not shouting at the TV loud enough. Swiper, no swiping. Swiper, no swiping. I mean, you're like giving it your all. You're in your like living room going, swiper, no swiping. And Dora's like, come on, help me. And you're like, swiper, no swiping. Because you're thinking this is not going to work. Dora's not going to hear me, right? And what happens on the occasional episode when you don't yell loud enough? Swiper swipes, right? You don't repel Swiper. Okay, so in this case, we didn't yell loud enough, and here comes Swiper. Watch, he comes in, and what did he do? He didn't take a hole, right? He took a point. How much dirt is in a hole that's 3 feet wide by 3 feet long by 10 feet deep? None. It's a hole, right? You can't take a hole, right?
I should have said a lot of nothing.
A lot of nothing. Swiper swiped a point on the graph. He removed. Would you be okay with, instead of saying swiping, which kind of has a pejorative context, like he stole it, he removed a point on the graph, yes, thereby causing a discontinuity. Guess what we call that? The formal name is a removable point discontinuity. That's a beautiful name for something that used to be there as a point that is now removed, causing a discontinuity. That's a removable point discontinuity, okay? All we have to do, here's why it's removable. This is why we call it removable. It was removed. Therefore, all we have to do is get that point back from Swiper, right? Chase him down and beat the crap out of him, get that point back. You never saw that part of the show, right? That was on the after show, where she went and got her cousin Diego, and they tracked down Swiper. Baseball bats, right? They even sometimes got Steve's help from Blue's Clues, right? Diego, go, Diego, go. You get the point back, and all you got to do to make this thing continuous again is put it back in its place. That's why it's removable. Swiper took it. Now, the reason we call it a hole is because he really only took a single point. How thick is a single point on the graph?
Not very thick.
Not very thick at all. In fact, it's infinitely small. We say when something's infinitely small, we call it infinitesimally small. Infinitesimally small. Okay? So you don't want to actually draw the hole to scale, do you? Because if you try to draw it to scale, it's going to look like it's continuous there, right? Because a point is infinitesimally small. So what we do to accent the point that was missing is we put an open circle, okay? Just like we put a solid dot somewhere else maybe to accent a point. This just draws attention to it. We put an open circle, okay? Now, if we were to get the point back from Swiper, right? So let's say we didn't beat him up. We just found him and we appealed to his better side and he relinquished it and gave it back. All we got to do is put it right back there and the graph is continuous again. He removed it. Now we put it back. That's why it's called a removable point. Why is it called a point? Because this originally had the point C, F of C, right? It had a coordinate. I know exactly where it was. It was at C, F of C. He took it. If we can find it, we can put it back, right? There was a point at C, F of C. Now there's a hole at C, F of C. See that? There was a point at C, F of C originally, and then he removed it, and now there's a hole at C, F of C. This is a removable point discontinuity. Or a what? A hole. Yeah. So the open circle that we draw there, it looks like a hole, right? Like if you were walking along a path, and you're looking down from above, and you stepped into there, you would fall down. You would fall into the hole, okay? So that's why we call it a hole. All right. The other type of discontinuity is a vertical asymptote. And of course, we draw it like this. This is not actually part of the graph. We draw it like that to draw attention to it. There's only two things the graph can do now as it approaches a vertical asymptote. It can either increase to infinity or it can decrease to negative infinity. And it could do either or neither on either side, okay? Does that make sense? It could do either or neither on either side. So that means on the left side, it could either go up or down or not exist. And on the right-hand side, it can go up or down or not exist. There is a graph that only lives on one side of its vertical asymptote. And you'll study that when we get to logs. But most functions live on both sides of the vertical asymptote, and that's why it's a discontinuity, okay? That's the ones we're interested for now. So assuming the graph lives on either side, it can do one of two things. It either goes up or down. To infinity, or towards infinity, I should really say, right? Towards infinity. So we call this a non-removable instead of removable. Why is this a non-removable? Let's say I beat Swiper up, or I just ask him for it back, and he's a nice guy. He didn't know it belonged to anybody, and I get a point back. Is there anywhere I can put that point on this vertical asymptote to make this continuous? No. Even if they went up on both sides, I couldn't put it anywhere to make them connect because they would continue going up. So that's why this is non-removable. Got it? Removable means I can put it back, right? Put it back, make it continuous. That's removable. Non-removable means can't put it back to make it continuous, right? Can't make it. So that makes it non-removable. All right, so what makes this one an infinite? Yeah, Brady.
Because it extends up and down. It's not making it infinitely close to it, but never touch it.
Oh, well, that's not why it's called an infinite discontinuity, but you're right. As you approach from left to right, your x values, if we call this value x equals c, your x values can get infinitely close to it from the left and from the right without ever getting there. And that's kind of a weird thought, because if I start walking towards that door, I'm going to eventually hit the door, right? But in this case, this is like someone that's always walking towards the door. They're constantly moving in that direction forever and ever and ever, but they're never going to get there. That's kind of a weird idea, right? Kind of. It's more like, think of the penalty in football when someone jumps offside and you're within your own 10-yard line. You're backed up deep in your own territory. Someone jumps offside, right? You're backed up deep in your own territory. If you're within 5 yards of the goal line, it's no longer a 5-yard penalty. It's half the distance to the goal. So let's say you're on the 5-yard line. Someone jumps offside, half the distance to the goal. The ball is now on the 2.5-yard line. Someone jumps offside again, half the distance to the goal. Now the ball is on the 1.25-yard line. Imagine that this guy can't get the snap count right and he constantly jumps offside. Half the distance to the goal, half the distance to the goal, half the distance to the goal. Will the ball ever end up on the goal line? No. In theory, it won't, right? Now, it's going to get to a point where the referee is going to get frustrated because he can't physically move the ball any closer without it getting there, right? Or the coach is going to eventually pull the guy that's jumping offside out of the lineup, right? But in theory, you can always go halfway towards something and then halfway towards that distance and half again, and never get there. Because just imagine like your secret ability to zoom in. I'll hold my hands like 2 feet apart. Half that distance is 1 foot. Now zoom in. I zoomed in now. It's twice as wide. Half that distance is now 1 unit. Zoom in. It's now twice as big. Zoom in, half, zoom in. See that? So I can keep doing that forever. In theory. So that's what's kind of happened here. So I'm glad you mentioned that, Brady. That's an interesting thing. The reason this is called an infinite discontinuity, though, is because look what the y values are doing. As the x values get infinitesimally close to the vertical asymptote, the y values either increase without bound towards infinity or decrease without bound towards negative infinity. That's why they're called infinite, okay? So non-removable means can't put a point down to make it connect. Infinite is because the y values go up or down forever. And of course, why is it a discontinuity? That's obvious, right? As we sketch from left to right, we can't get to the other side without lifting our pen or pencil, okay? Just like with the whole. So they're both discontinuities, but the whole is the only one that's going to be removable. We're going to talk about jump discontinuities later, and they're also non-removable. The whole is the only one that's removable. That's the only one that you can put it back on that single point and make it continuous. None of the other discontinuities you can repair, all right? So vertical asymptote is what we call that. It's the only asymptote that is a discontinuity. Remember that. There are other asymptotes, but it's the only one that's a discontinuity. So when you get division by 0 for these types of functions we're going to study, it's going to be one or the other every time. Your job is to figure out which one it is. Now, it would be easy if I just let you have a calculator, right? And you were able to type in the equation of the function and hit graph. You could probably spot this on the calculator. The calculator, the new calculators don't they don't draw vertical asymptotes. They would just leave it blank, but you could tell, right? The old calculators tried to connect the lines. So when you drew this on an old calculator, it would kind of look like a heartbeat. It would try to connect the dots. But new calculators, I think, just leave it blank. And of course, a whole is going to be really hard to tell on a calculator because the calculator typically connects the dots. It doesn't leave a little break there. But you're going to learn how to figure out which one is which without a calculator. That's exciting, isn't it? Yeah. We don't need no stinking graph, right? We don't. We are the computers, right? So let's see if we can squeeze this one in here. Find the domain of each and then classify each value that gives you division by 0, known as the discontinuity. Classify it as a whole or a VA. All right, let's look at this guy here. We can spot the domain now very quickly, right? We set the entire denominator not equal to 0, and we get x can't equal 2. And that's it. So the domain of f is the set of all x such that x is not equal to 2. Okay, so the domains are going to start getting a little bit easier now. Is 2 then a discontinuity? Well, hang on. X equals 2, first of all, is a discontinuity. Okay, it is a discontinuity. Why? Because it gives you division by 0. It's real easy if you're not sure. Just think to yourself, x can't be 2, but x can be 1.99999, right? And x can be 2.00001. So this function and this graph live immediately and everywhere to the left of 2, and this graph lives immediately to the right and everywhere to the right of x equals 2. So when you're sketching the graph and you get the 2, you got to step over. It's an interruption in the graph. It's a discontinuity. Now, Brady, you said it was already a hole. How did you know? How did you know it was a hole already?
X cannot equal 2, meaning that all values on the line that would be 2 could not equal it. Thus meaning it would create a hole. It's not an equal to. Like, take the greater than or equal to. Sorry. It's not any greater than or equal to. It's just a greater than. It's kind of like that.
Interesting analysis. Did you learn that in Algebra 2, or is that coming from your own, the world of Brady's mind?
It's coming from my verbal explanation.
Okay, well, here's the deal. I don't know if that's a legitimate explanation or not, because I really was having a hard time understanding with the inequalities and stuff. But in your mind, it makes sense. But look, I'm not even sure yet if it's a hole. Here's what I'm going to tell you. It's going to be either a hole or a vertical asymptote. It's going to be one of the two. It's going to be one of the two. Now, to figure it out, I'm not sure that you can just look at it like this unless you have this weird gift, and weird meaning like cool, okay? I don't want to like cast you out as like, but it's hard to tell when it's like in this form. The easier form to determine is when it's in factored form. Now, we are going to run out of time today, but when we get to class tomorrow, the first thing we're going to do with this function is F it, right? We're going to F it. And when it's in factored form, you'll see that it's then super easy to determine if it's a hole or a VA. And Brady, you may end up being right. Time will tell. Your reasoning, though, if you are right, it might just be a little bit of fortuitous happenstance. Okay? All right. Y'all have a super great day.